So when you plug in the 4 up here, you're going to see that's 21. So let's go to 22. Close. Okay, so we are looking from 0 to 4. So if I want to put in bars there, write in x. Oops. Let's put in x equals 0 as one y-axis. That's already there. That's the y-axis. And I'll put in x equals 4 as my other boundary. So what am I really looking for? I'm looking to say, if I had this kind of a shape and I were to flatten it out, where would it flatten out to? That's what we're asking right now. Okay? Well, that's what we're asking. So we want to know, what is the average height of this function? So here, what's the height?
1.
1. And here, what's the height?
21.
21. So if it increases at a constant rate, what is the average height of this function going to be? You're the closest. It's not 10, but on that track.
11.
Why 11?
Yeah.
I would do that when you get the integral.
Because that's what you got the integral?
Yeah.
Guys, what's the height here again? 21. What's 21 plus 1?
22.
Divided by 2? 11. Because this is constant, so it's just the average.
I thought 20 divided by 2.
Whenever, that's exactly why you're the closest there. If you do 21 and you subtract the 1, you get 20 there. So the idea is this. If you have a linear function, the average value of the function is the average of the endpoints. So since this is 1, and since this is 21, it's 22 divided by 2, which equals 11. So here is what it would look like if you were looking at the average value. And you guys all did the integral and you got 11, right?
Yeah.
Now, the next question becomes this. On the AP exam, here's what they ask. Here's what they ask. At what location does the average value of the function meet the actual function? So what are they asking for? 2. This is 2. Again, at what location or where is the average value of the function equal to the original? Here's the average value, here's the original, there it is. So if you're ever doing this, look for the intersection. You okay?
Yeah.
Okay.
So you don't
I
have
thought
to
you were
say-
choking, I really did, I'm sorry.
So you don't have to say 2 at 211? You just say 2?
This would be 211.
Yes.
But if they said,
They say location.
if they say what location, it's just going to be 2. If they say what is the value of the function, it's 11. What is the height? 11. What is the width? 2.
So what if they ask for both?
What is, at what point? At what point? Again, 2 is considered to be like the width or the location, where h is considered to be the height, okay, or the value.
I thought you said,
Again, those words are very important.
I thought
This
you
is,
said 2 was the right.
no. 2 is, the value of the function is 11. The location at that value is 2. The width of the function here, up to here, would be 2. The height of this function is 11. Okay? Are we clear on this?
Yeah.
Okay, it's very important that we understand this. So, with that said, what happens if you don't have a graph? Let's go back to the example. Okay? This one is not going to be graphic calculator.
No, but I did that one once you call with you plug in the 11 to the equation, you get 2.
Yes, that's exactly right. Very good.
Can I see you?
So, take a look here.
No, we didn't get to say it yet.
I know.
No, no.
I
only use a finger.
I don't even know where it is.
Okay, so this is what you all did. You got the average value of the function. You did the integral over 1 over 4. Sorry, 1 over 4, not 2. 1 over 4 times the integral from 0 to 4 of 5x plus 1 dx, you got 11. That's what you got, right?
Yeah.
Now, if the problem says what location, you take the 11, which is the average value, plug it back in, and find the location. So say 11 equals 5x plus 1, subtract the 1, 10 equals 5x, x equals 2.
And that would be the width.
X is, yes, very good, the location or the width of the function. Okay? All right, with that said, let's start something new. Same idea, integrals again, but we're going to look at more applications. Integrals are going to pretty much be all applications. Okay, there's going to be very little that aren't applications. Even though we start another topic that's called application soon. They're all going to be like this. So for this example, what I'd like to look at is
I can't.
Recall, what is the right?
You should know this already, but I'll write it on the board in case. Remember this from derivatives.
Yes.
Oh, no.
So, we're going to use this today to help us. We're going to use integrals, but you got to remember what this meant.
Oh, yeah.
Remember, x is what? Good?
Velocity.
Good?
Acceleration.
Good. So, this tells us velocity is the derivative of position. Acceleration is the second derivative of position or the first derivative of velocity. Either way. Remember the order. It's always x, v, a. Now, for integrals, what are you going to say?
AVX.
AVX. You're going back up. So since the velocity was the derivative of position, the integral of velocity will get you back to position. Again, if you have the velocity, you want to go back to position, you got to go up a level. That's the integral. So the next thing we want to start writing is this. Position is equal to the integral of the velocity function from a to b dt. Why dt? Because my variable is now t. Okay? Remember, this is not x like an independent variable anymore. This is not your x like 5x plus 2. This is x of t, or the position function. Kenneth?
Actually, I was wondering, when you have like, so the integral at the end of the derivative, and we were graphing it before, do you have the, will they tell you exactly like what, how you integral, like will they tell you like which derivative it is so that you can go back to the original, so that you can graph it, or do you just assume? I mean, like you could, like let's say you were like on the.
You have to be given the velocity to find the position. Absolutely. Absolutely. You got to be given the lower one to go up. Yep.
What I mean is like, do they tell you like which lower one you're in?
They'll tell you the velocity function is this. With this condition, find the
But I mean
position.
anything, not just velocity
They'll
acceleration.
say the second derivative is this.
Okay.
Find the original function. You got to integrate twice. Okay. All right. Next, we know that the velocity, therefore, is equal to the integral from a to b of the acceleration. Okay? That's all we got, really. We talked about jerk as being the next derivative, but we don't even use it, so just don't even worry about it. Okay? If you study engineering, it is good to know what jerk means. Okay? The idea, it's mainly used in aeronautics, so planes and stuff, because you have force, thrust. So like rockets, remember we talked about rockets, where it's the force of thrust is propelled down? Okay? All right. Now, let's start with a very basic example, and then we'll get to the complex stuff that's on the AP exam. If
No, let's just shorter this year. They shortened the lunch this year by 6 minutes. What? Like our lunch actually like 27 minutes.
Are you sure?
Yeah, it shows it even on the schedule.
Only lunch C, you mean?
Huh?
Only lunch C or all lunches?
All lunches.
Ah, you mean yours is short. If the velocity, yeah. If the velocity function v of t is equal to 5t squared minus t, then determine the change in position from time 0 to time 5. Okay?
No units?
You're right. You're absolutely right, sir. Thank you. Appreciate that.
When you go, do you change a variable? You change a variable when you go up? I forgot.
As opposed to...
No, that's when it's two different variables.
No, because if you're like,
What do you mean change the variables? I don't
Like,
understand.
if it was VX and then it had T inside,
I don't know, it's just like,
Okay.
when it comes up with specific.
Velocity, position, and acceleration are always functions of time, no matter what. It's always going to be t. Okay? So here, we're asked to find the change in position, right? Change in position. Remember that reading I had you do the other night? Does this ring a bell now? Comes right from there. So here, for this kind of a problem, I want to know what is the position of the function at one part and what is the position of the function at another part. So I want to know the change in position. So think back, guys. Remember when you take the integral? After you take the integral, you plug in the upper limit, you plug in the lower limit, and then you subtract the two?
Yeah.
Isn't that what the change is? Subtraction means change. Change in height from when you were a kid to here. You take your height now, you subtract your height then, that's your change in height. It's the same thing. So the integral can be thought of as the net change. So you want to write that down. The integral can be thought of as the net change. It's called the net change theorem, which was what your reading called it.
Do we have to call it net change?
I don't think they'll ever use the word net change theorem. They would give you a problem like this, just like this. Part 1, no calculator. That's the problem they give you right here. Okay? One thing they always do, they give you very easy functions when they do velocity and acceleration and stuff. The only time they give you difficult ones, sines and cosines. But that's just memorization. Knowing the integral of sine is negative cosine, the integral of cosine is positive sine. Okay? That's what they do a lot. Because a lot of particles vibrate, and vibrations are consisting of sine and cosine waves. And later on in physics, if you're in class, you'll learn when we get to vibrations, you're going to see the actual wave looks like a sine and cosine wave. Some of them are higher and lower, higher frequency, higher amplitude, lower amplitude, but generally vibrations represent motion. So here, if I want to find the change in position, it's pretty much saying, what, Kenny?
Go back to x.
Good. So it's saying, figure out what x of t is. Well, I want to know what x of t is from where to where? From really 0 to 5. That's what it's saying to figure out. Well, the definition of this is really just the integral of the velocity function from 0 to 5. Again, if you can find the integral of this, it gives you the position. Then you're going to plug in the 5. Then you're going to plug in the 0, which is what this is saying right here. Again, integrate this, dt, with respect to time, plug in the 5, plug in the 0. That's what this is saying on the left over here. Again, those say the exact same things. What you need to know, okay, what you need to know is that the problem is asking you to do this, but you want to really write this. Again, if you're finding a change in position, you find the integral of velocity at your limits. If you're finding a change in velocity, you would find the integral of acceleration on its limits. So let's go ahead and integrate this. So we're looking at the integral from 0 to 5 of 5t squared minus t dt. Again, this is the velocity, so when I integrate it, I get the position. If I then plug in the 5, I'll get the position at 5 seconds. If I then plug in the 0, I get the position at 0 seconds. When I subtract them, which is what my integral tells me to do, I find the change in position. So here, what's the integral of this going to be?
5t cubed.
T squared to second.
Over 2. You said the same thing twice.
Oh,
You said
times,
t squared to the second.
you say times, 1.
No, guys, that was average value. Guys, yesterday we did average value of the function, right? Today we're looking at the net change. Net change is not, there's no 1 over b minus a in the front.
Okay.
Again, this is new. I said there's a new topic. We're not using the average value theorem anymore. Okay, we're done with the average value theorem. Okay?
That's
So here, let me stop for a second to just answer a question I notice a lot of you are asking right now. Pause for 1 second. This is the position function. Again, this is the position function because this was the velocity function. And we know that the integral of velocity bumps me up to position. So that's the position function. If I plug in a 5, like this is telling me to do, and then I plug in a 0, and I subtract them, I'll find the change in my position. When I plug in a 0, though, what do I get? 0. So this is like saying the object started at the ground level, and it started moving up. Or it started at the origin, and it started moving to the right. So when I do this, maybe I should have done 1 to 5 to show you. You want to change the limits to 1, please? Make that a 1. Okay, change everything to 1. Just so you can see, guys, I want you to see that there's a position at one time, and there's a position at the other, and we're finding the difference between them. So let's go from 1 to 5 instead of 0 to 5. So please change those respectively. There's my spot checker. Nice. Thank you. So here, At this point in time, we're going to see. This is the position function. So this is the position of the particle at 5 seconds, right here. So please write this down. This is the position at 5 seconds. That's what that is. This is the position at 1 second. We want to find the change. That's what a subtraction sign is, right? And an integral, when we did the integral the other day, we took the upper, plugged it in, we subtracted the lower. So the integral is the net change. Again, the integral of this is the net change of it. So at this point in time, what can I do? Good, just simplify. Calculate.
Less 190.
625.
Here's just
The
625.
left side is 195.83 at the left side.
One what, Kenny?
195.83.
Agree or disagree? Thank you. Obviously agree with yourself, Kenny.
The other side is 1.1.
You said agree.
Yeah.
What do you got?
1.16666. Oh, there's also contiguous too.
What's that?
There's contiguous too.
Is there another one in there, Jess? Jess?
I got 1.6.
No one here, right?
Yeah.
Anybody else? You got 1.16? Josh, check again. So, this is my position here. This is my position here. So if I want to know what the change in my position was, I take my final position, I take my initial position, here's my final position, here's initial, and I subtract them. Again, we're finding the change in position. You also got 1.66?
It's 5/3.
I'm with you on that. Did you subtract this one over here? Minus 1/2?
Minus 0.5.
Did you subtract 0.5?
I got 1.
You got this? Okay. Josh, don't forget the 1/2. Okay. All right. So the change in position here is just a subtraction. So subtract them. What do you got?
194.6667. I rounded to the fourth digit.
You get 94.
I just got 0.67.
Should it really be a bar with the second one, Edgar?
Huh?
Should it be a bar?
I don't think so.
Okay, that's right.
I just
Now-
rounded to the fourth proposal.
Here's what I need to ask you. If I gave you in the beginning of the problem the statement this, if I started by saying,
So, Mr. Howe.
hold on. If I started by saying, if the velocity function is equal to this in feet per second, I should have put that unit there, because we have seconds for time, as usually reminded me. In feet per second, what would be the change in my position? What would the units be? Just feet. Again, remember, if position is feet, velocity is feet per second, acceleration is feet per second squared. If it was meters, it's meters, meters per second squared. So if you're starting with feet per second and you want to go up to position, it's just feet. And think about it. My position is here, my position is here. I've moved a distance of feet, not feet per second. Remember, so when you integrate something with respect to time, one of your seconds goes away. So if you had acceleration, which is feet per second squared, and you wanted to find the change in velocity, the change in velocity units would be just feet per second. Again, whenever you integrate, you're getting rid of one of your seconds as a unit. Whenever you differentiate, you're putting another second in the denominator. So my answer at the end should be not just this, but with units of feet.
Oh, and
Okay.
then
Say again?
it is going to be.
It is, thank you. In units of feet. Okay, it's extremely important that we understand what's going on here, because the next theorem we're going to learn in a minute is getting a little bit trickier. And it's not trickier in the sense that the math is more difficult. It's all going to be logic in this point here. The next one we're going to do. You got to use logic. And I'm going to do an example in front of you right now to show you what I mean.
Did it twice too.
Okay? So, let's go through an
If
example.
Alice is logic 3 times in a row, it means it's logic.
Here, if I'm standing here, those of you in physics know this, please sit quietly if you understand what I'm going to do. It's fine. If I'm standing here and I walk to the desk, I would say every tile is a foot. They are. They're 1 foot by 1 foot.
Really?
Yeah, they are. Square feet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So when I walk from there to the desk, I walk 13 feet. Agreed?
Sure.
So my change in my position, also known as my displacement, please write this down. Delta position is called displacement.
So delta
Okay.
P?
Delta position is called displacement. Don't call it P, write position, or delta X. Okay? Again, delta X, which is my change in position, is also called displacement. D-I-S-P-L-A-C-E-M-E-N-T. Okay, displacement. Sorry?
What's the word you got? Assist. No, not assist. Assist. What? Huh?
Velocity is slow.
No, displacement is called. No, assist. Whatever you have in your back, it's like can't get.
If you have a position graph, and you're looking at two positions, the change in them is the displacement, but it has nothing to do with the slope. Nothing to do with the slope. The change, not the slope. The slope is always derivative. Now, back to the example, please. Listen. If I walk from my spot to the desk, my displacement is 13 feet. Everybody agreed with that, right?
Yeah.
Now, if I walk to the desk 13 feet, listen, focus, please. If I walk 13 feet, then I walk the same 13 feet backward.
Zero.
Edgar, what is my displacement?
0.
How come?
Because you're back at the initial spot.
Have I changed my position? Even though I walked forward and came back, my starting position was here, and my final position is here. So have I changed my position? No. So my displacement is 0. Listen. What is my distance traveled?
26.
26 what?
Feet.
Feet. Again, I walk 13 feet, and then I walk 13 feet back. Distance does not have units. I'm sorry, distance does not have a magnitude, negative or positive. It's not a vector. So for the problems we're about to do, displacement is what we just calculated. That's what we just calculated, the displacement. But the distance is not necessarily the same. Let's discuss. A minute ago, or sorry, a class ago rather, we talked about how the integral is the overall areas, right? Overall areas. So if I have a function like this, and I go from A to B, A being the origin, B being the final, my overall displacement is the integral. If this is velocity, remember a minute ago we said the integral of velocity is displacement, or change in position. So the integral of this would be, say that's 5, let's say this is 2, and let's say this is 10, the areas, okay? The integral would be what? What would it be?
No, that's 13.
No,
13. What is this area, guys? It's considered a negative for integral. Remember, the integral of v of t here, the integral of this function from a to b is 13. How come? You take the positive areas and you subtract the negative area. Remember that. So it's 5 and 10 is 15. Again, minus the 2. But that would be my displacement. Again, this would be my delta x, or my displacement. But my distance traveled is really the absolute value of the sum of all your displacements. So it's 17 then. So again, here's what happened just now. For this velocity function, somebody did this. I'm going to start back here. They walked, what's the first area, 2? 5. They walked 5 feet, went back 2 feet. Then they walked another 10 feet forward, giving a total displacement of 13 feet. But the distance I just traveled is the sum of all the positives. I walk 5 feet, then I'm walking a distance of 2 feet, so I'm at 7 feet now. Then I walk another distance of 10 feet. So altogether, I just walked 17 feet. But my net position change was only 13 feet. Again, my distance traveled is 17 feet, but my net position change is only 13 feet. Do we see the difference there? Now, the AP exam uses this all the time. So here's what you have to think about. If you're doing this analytically, what you need to do is the following, guys, and this is where it gets very tough. You need to figure out this location. Those are the roots of the function to tell when you need to change up your integral. So what you need to do on the test is this. To find the distance traveled, here's the formula for this example. You would do the integral, let's call this x1 and call this x2, the roots. Remember x1 and x2 are your roots? We have to find the integral, those are the roots right there, from 0 to 5, or from a to x1, from here to here, find the integral of v of t dt. Next, to that you have to add what?
The integral of x1 and x2.
But what do you have to add? Not x1, absolute value. Because what is this integral going to give you here? Isn't it going to give you negative 2? Remember, the integral will give you negative 2 here. But when we're finding distance, we want to think of this as a positive thing. So you add the absolute value of the integral from x1 to x2 of v of t dt. And then to that you add the integral of the last part without the absolute value. But here's the key, guys. Who cares? Who cares whether it's below or above? Put absolute values around everything in between your plus signs.
Just to be sure.
Just to be sure, exactly. Integral from x2 to b of v of t dt.
But you only have to do it for negative.
Houston, you're 100% right. This is going to be a positive distance. This is going to be a positive. This would end up being a negative, so it only matters for the middle one. But to be safe, we want them all to be positive, don't we? Do you want to have to figure out which is above, which is below the axis? No. So find the roots, use those to break up into a piecewise function, and put absolute values around all of them. Because you know what, Houston? Take a look at this graph right now. Wouldn't that be the exact same location for the roots? So wouldn't you break this up the same way? And now you need the absolute value of this part. You would not need the absolute value here, but you would need the absolute value there. So to be safe, to generalize, we say, break up the function into its pieces based on where the roots are and put absolute value around each piece. Okay? Again, break it up into its little pieces. This is where piecewise functions come in. Okay, this is where piecewise functions come in. You're thinking about it as three different things. Granted, this is the same function. We're partitioning it. We're breaking it up. You could be given a piecewise function, and we'll talk about that in a little bit, how to do that. So let's do an example of this. And I want to do an example. Oops, I didn't mean to do that. Let's undo. I want to do an example now that has a part above and below the axis. Okay?
Does that have a function?
Yes, but I want to make a function up now. I just call that v of t. But let's actually do one mathematically. Okay? If v of t, let me get my example so I don't screw up the total. If v of t
The clock's not working.
it should be working by now. Yes.
They're actually 10 minutes behind, so technically,
No, I
it's
never did.
4:50. I mean, 12:50.
Why are you going to this? What is the burn? Yourself.
Wow.
Keep writing the how, and I'm gonna learn.
If v of t equals t cubed minus 10t squared plus 29t minus 20, where v of t is measured in meters per second, find this is a very good example of a part 2, by the way, guys, and it would be a little bit more than just the two things we're going to do now. It would be a third. There will be a third case also to find. I'm just going to put the first two here.
It makes it serious.
Find the displacement from let's say instead of from, I'm going to use the exact words here, on
I mean, you're the one that was like,
time interval
like, you'll see somebody who's peaceful saying that. People who's peaceful.
from 1 to 5, okay? From 1 to 5. Now, I don't need to put units here, because what are my units by default? The units of velocity are meters per second, but what is the units of this going to be?
Seconds.
Seconds, because why, Carrie? What is this?
Time.
Time.
Did I say less than equal to, less than equal to?
Less than what?
Or equal to?
Less than or equal to, less than or equal to. So between 1 and 5. All of you guys should have. Now, also find the distance. Okay? So the displacement and the distance traveled. Sorry, I should put the word traveled. Okay, on the time interval 1 to 5. They're going to be different, guys, just like I showed you. My displacement before was 13, but the distance I traveled was 17 meters. So we got to figure out, this. We got to start by figuring out to ourselves, where does this go across the axis? Where is it going to be a partition? Remember the last example, we broke it into 3 parts, right? Because it crossed the axis twice. We got to see if this crossed the axis at all between 1 and 5. Now, you can't graph it, guys. So don't look at the graph. I know you did.
No.
Okay, don't look at the graph. How do I find the roots of a cubic equation?
Synthetic.
Synthetic.
I have my hand up.
Sorry.
I have my hand
Sorry. I'm trying to give other people the time to think. Some people said it. Synthetic. Thank you for raising your hands, guys. Okay, so taking a look at this function, start your synthetic table.
You can't.
Non-calculated. Easily non-calculated. Because the numbers work out to be very simple here. Okay? So here, they do.
Decimals. Exactly.
Okay? Why are those my headings, guys? What are they? They're the what?
Constant.
Coefficients. Constant coefficients, that's fine. They're not constants though. Constant coefficients or coefficients.
We go to 1 and 5?
What do I start with, guys?
1.
Always start with 1. You always try 1. If the signs alternate, you hit a bound. If the signs are the same, you hit another bound. Remember that? If they're alternating lower bound, if they're the same upper bound. So use that to help you. Start with a 1. You bring down the first number. 1 times 1 minus 10. Negative 9 minus 29.
Like,
Hold on. No, it's plus 20.
Sorry, negative 9 plus 29. 20 and negative 20.
0.
So, is it one of roots? That's one of my roots. Do I want to keep doing this?
Yes.
You don't have to, right?
No, you don't, guys. Come on, think about your tricks.
Quadratic?
Bring that down to a quadratic, remember? We started with the cubic.
X minus 1.
Whenever you get a root, come on. Whenever you get a root, the row that is left are your coefficients of your quadratic if you started with cubic. If you started next to the fourth, which you wouldn't, okay, especially if it's non-calculator, you start next to the fourth, then it would be next to the third, you'd have to do it again, make another table with these numbers. Factor,
X minus 1. X minus 1.
very good, Kerry. And they're t's, not x's, I apologize. They should all be t's. That's my bad.
So the roots would be negative 1, 4, and 5, right?
schools that I can't even in school.
I would write t, Jasmine, because x is the position. X is the position, always, okay?
Wait.
What's up?
What does this tell us?
This tells us that it crosses the x-axis at 3 locations, 1, 4, and 5, which is all we'll have, because it's cubic. So now, just to show you guys, now that we've got it,
But isn't that just the
now that we've got it by hand, let's do it with the graph. Give me a second, Kenny. The graph will look like this. It's on the paper that I handed out to you. The graph will look like this.
The packaging.
Take a look. I am interested in the integral from 1 to 5. From 1 to 5. This is what the actual graph looks like. And doesn't that make sense now? Isn't this going to be a positive area? And what is this going to be? A negative. So when you use displacement, you can simply do the integral. But when you want to find the distance, you got to break it up. Do the integral to 1 to 4, absolute value, even though it's positive, do it to be safe. Then do the integral from 4 to 5, absolute value. Add them up to get the distance traveled. Remember, this is the velocity function. Okay? Jasmine? Say one more time.
I didn't know up and down.
This is above the axis? Positive area? I'm showing you. You don't need to know this. This is what it looks like. You will not be knowing this because of the graph. So, All I'm saying is this, I'm trying to show you guys what you're doing. So when you want to find the displacement, you're just simply going to do the integral from 1 to 5. But now for the distance traveled, do the integral from 1 to 5 plus the integral from 4 to 5, all with absolute values around them.
4 to 5 because that's the root.
Yes, exactly. Because the 4, the 1, and the 5 break it up into its parts. The 1 and the 5 happen to be the endpoints, so those roots don't really matter. But the 4 does. When it crosses the axis at 4, this becomes a negative area. But if I want the distance traveled, I want that to be a positive area, and I want this to be a positive area. But for the displacement, this positive and this negative are going to counteract.
Isn't it 1 to 4?
Yeah. Shouldn't the one integral be 1 to 4?
Yeah.
Yeah, I'm sorry. Why did I put 5? I'm sorry. Thank you. Okay.
You put 5 in.
Oh my gosh.
Wait, hold on, why are you putting 4?
Because it's just halfway. Remember what we did before?
Halfway.
Oh, whatever, it's a piece
It's a
of
partition.
partition.
Use your words, right? It's not halfway though, right away. We want to find the distance traveled. This will give me a positive distance or displacement. This will give me a negative, but I don't want it to be negative, so I'm breaking it up into those parts.
You kind of confused me there what you said.
Sorry.
I know, right? you start seeing these random symbols. Right.
You have the question.
Okay? So again, that's the displacement, that's the distance traveled. At this point in time, I'm not going to go through the calculation, I'm going to give you the answer. You guys know how to do this by now? The cool part is if you could use your calculator, you can just type in the function and use the integral on it. Remember I showed you that the other day? Press second calculus, go down to integral. We did that. You could do it that way also.
Just to make sure I'm on the right track. So from here, you were just put down the interval and then just plug in.
Absolutely. So the integral you get here, doing this, when you plug it in and you do all your math, it's on this worksheet. I gave this to you. If you want to look, it's on page 292 on that little packet I had you read the other day. On the bottom, the integral for the velocity becomes a displacement of 32 over 3, which is 10.6 repeating. That's my displacement. The distance traveled, though, is 71 over 6. That's going to be 11.833.
71 divided by 6, 11.833.
Oh, okay.
And in case you're wondering, this portion, when you do the integral of this one, turns out to be 11.2.
You say that now. Give it one more section.
Okay, 11.2, and this one turns out to be 0.63. Yes, and that makes sense. Okay, again, look, if you do the integral of this one, you get 11.2. Now, please remember, guys, take 11.2 and subtract this number. You get this number here. Again, take 11.2, approximately, guys, approximation. If you subtracted this number, that's what the displacement is, because this is a negative area, really. But if you think of distance, you need to add this number, so you get that value. So look at your two things here. Okay, look at the two of them. Because there's only two portions of the graph, because if there were three, this wouldn't work, what I'm about to say. Because there's only two portions, the average of these two just turns out to be this one here. Think about it. To get this number, you're adding this. To get this number, you're really subtracting this. So because it's in two pieces, only because it's in two pieces, like I just said a second ago, this happens to be the average of these two. If it was in 3 or 4 pieces, it wouldn't work that way. Okay? Thank you. So here,
The average would be 11.2.
the average would be, but they're never going to ask that. I'm just putting a side note. They're not going to ask that part. Here's what I want you to notice, though. Which is bigger, displacement or distance? Which is bigger? Distance. Distance. Look at the number, guys. Distance is 11.833. Displacement is 11.6. It will always be this way. Think logically. It's always got to be. Because displacement, sometimes you have negative areas, right? And they're going to take away. But distance, aren't they always positive? So here's what you want to write down as a conclusion. Distance will always be greater than or equal to, because it could be equal, if everything's above if it's always above the x-axis, your displacement and your distance are the same.
Linear?
Okay? No, it doesn't have to be linear.
I mean, I'm saying one example of
No, linear could be below the axis.
But on a range of 1 to 5.
Stop.
On top of the world.
Except that you're wrong there, Kenny. Once I'm wrong too sometimes. Okay? It has nothing to do with linear or squared or cubic. It's if f of x is greater than 0 if it's above the x-axis. That's the condition. So, this is always correct. Now, how do you write this algebraically? Here's how you write this. The integral from a to b of v of t dt, absolute value, is always greater than the integral of a to b of v of t dt. Okay? Again, the integral of the absolute value of those areas is always going to be greater than the actual integral of the other one. That's exactly how you would write it. Because remember, distance, we're using the absolute values. Displacement, we are not. Now, my question for you guys is this. We have 10 minutes left. I'm going to give you an example to work on. But I want you to think. Just now, we did velocity given, find displacement, and find distance. If you're given the acceleration, you're going to find the velocity versus the speed. The speed would have the absolute values now. The velocity would not. Okay, so again, the one we want to make another conclusion about is this. The velocity, sorry, let's write it backwards, sorry, I wrote it backwards. The change in speed, okay, the change in speed, also known as the distance traveled in that sense, if you want to think of it, will always be greater than or equal to the change in the velocity. Okay? The change in speed always be greater than the change in velocity.
So,
It's like the idea of distance and speed being related and displacement and velocity. If you're in physics, you've seen this many times. X and V, we call this D and we call that S. Okay? Remember that.
For this, is it the same exact, like, steps and everything, just changing pretty much words?
And that's what I'm going to give you an example to do right now. Okay? The example now is going to be given acceleration, find the change in velocity, find the change in speed. Okay? Again, find the change in velocity, find the change in speed.
Never raised my hand again.
absolute value.
I have my hand up 4 times. Ask a question about the last problem.
And did I answer every time?
No, you went to Jasmine, who had her hand up after.
Okay, what's up?
Velocity?
I'll ask later. 'Cause I
No, no, go back, come on.
What is speed?
I'll do mine.
I was wondering about like the beginning of the problem with was like 1 and 2. So if they ask you about like looking at it as an acceleration and say that actually like acceleration, I was actually they said acceleration and then like displacement, you have to go to you have to do the derivative to go to get the acceleration and then do the integral to get
Sure.
the.
That could be a good example. Given velocity, find acceleration, and then you need to know derivative and integral. Yeah.
When you're looking at the time interval of displacement, like of each one, do you have to do a graph of each one? Or, you know, how get seconds, right? Time
No.
interval of 1 to 5, and you were looking at.
And I showed the graph here.
Yeah, you have to do it of each one if you want to find like. I mean, I know it's just like to help you look at it like graphically.
But if you don't have a graphic calculator, then you wouldn't have it. That's what I'm saying.
But if it's a non-graphic calculator, you could do it in a way, in a certain.
Sure, you could sketch it yourself. Yeah, absolutely. That does help sometimes. You don't have to though. You can just go right to the formula.
And you need to find the roots of each.
Absolutely.
Each of the tests they give you both derivatives and integration.
Yes, sir. Absolutely.
Yes, I can.
Well, here, take this look. Here's what they might say, just to trick you up. Look, they'll say this. But x double dot is acceleration. It means the second derivative, remember? Second derivative is acceleration. So they can write it that way, or they can write v dot, because that's acceleration also, or they can write a. You got to know every interpretation is up for. Okay? So, this is given as calculator allowed. Calculator allowed.
No, you're talking about the x and b.
Calculator allowed for that reason. Calculator allowed.
What sign is the opposite of both sides? Opposite,
One back one, right here.
Yeah,
right? Opposite's close, right? So what is the T and the T?
It just stays in there. It doesn't touch it. Actually, I haven't gated touch it. I did not. He just looks at me like I instigated.
No, I would be like, I think you got that.
Wait, that 2T doesn't.
need to
I think he
enter.
does touch it, doesn't he, Aaron?
I'm talking about touch. Stop.
Do you remember how long it
Is your number ready?
Need an entry.
I mean,
Your first chamber?
how flat last
It's
week?
divided by TCS and anything else?
Gosh, that was.
Can you give me a second? I'm in the middle of typing something.
I hope you can, because he's like, it's because
That was my question, actually.
he's like, unless.
Wait, that was my question.
No, that was.
No, it was my question.
Oh, wow.
Yeah,
Thank
you can.
Okay.
And
Where's your graph?
Oh, go to Trace and put axis on.
He's gotta look extra.
Wow.
I forgot which one it is.
Man.
X-axis.
Format.
Smaller babies.
Wait, where's your integral from?
I'm working on it. I'm trying to figure out a good one for this.
I felt like it.
Nice. Okay. Great problem.
Now you just have to use complicated.
I
Now, I highly recommend, first, use your calculator. Second, you're going from 0 to 1. So please, zoom in. Because if you look at it like this now, you're going to see it doesn't look that good for you to work on. Zoom in,
See it,
please.
could you just like.
Okay? You'll see, you have your own.
Yeah.
So again,
Speed is the absolute value, right?
remember, you want to figure out the integral for velocity. Then you want to figure out the integral on each part for speed and add those areas up. Use your calculator to do that. So you need to know what the root is of this between 0 and 1. So you might want to start by graphing this, go to your calculator, press second calc, find the 0 of the function between 0 and 1, and you'll see that there's one of them there. When you see that happen, you'll be able to see the graph of this from 0 to 1. Again, zoom in on the graph from 0 to 1. You're going to see that it comes down. Edgar, does it come down like this somewhere? Or does it go up? Does it go down or up? Which
Goes down
one?
like a little bit, like barely, and it goes back up.
And then it goes back up?
Yep.
So there's more than one intersection? Root?
2.
There's 2 roots. Oh, nice, even better. So it looks something like this, Edgar, right? If you zoom in enough? That's weird. You gotta zoom in further on your y-axis. Yeah, your y-axis is going 10 to 10. Why? Go from like
I gotta give you one to do
negative 2 to 2.
Who do you watch out there?
my gosh, give us a look.
How do you watching up?
A little bit.
What is that increment right there? What are your increments going by? So there's only one intersection, guys. There are not 2. So be careful. This cross is at 0 here. Why is that? Because if you plug into 0, sine of 0 is 0, 0, 0. So here's what I want you to do. Listen carefully. That's going to look like this. Sorry. So remember, for overall velocity, you're finding the integral from here to here. So press second, calculate, and just find the integral from 0 to 1. It'll take this as a negative and this as a positive. It'll give you the change. For speed, you got to find the root, find out that area, or find that integral, then find the integral from here to here, find that integral, add those together on your own. Over the weekend, I'm going to give you some work to do. I'll bring you down for lunch. Okay? Same kind of problems. Same kind of problems.
First time, yeah, that's not a lot.
Celebrate.
I mean, it's a lot.